Imagine you want to examine the effect of the level of democratization in the world on the amount of civil conflict. First, of course, you work very hard to collect your data set. You collected your dependent variable as the number of civil conflicts in the world per year. And the independent variable is the number of democracies in the world per year. Now let's check out what the data looks like when plotted. At first glance, there are a number of observations one can make about these two graphs. First, both graphs show time trends. That means that the number of democracies in the world has been steadily increasing until roughly 1995, and then somewhat plateaued after that. The number of civil wars has also been steadily increasing over time until roughly the same time in the early 90s, and then has also somewhat declined. Thus, the data are ordered in time. In statistics, we'll call these types of data time series data. Now, time series data come in two types. Stationary, where the variance and the mean of the data do not vary over time, and non-stationary, where the mean and or variance vary over time. That means that we can have one without the other, or both of them at the same time. Can you identify which type of time series data we deal with here? It appears that we are most likely dealing with non-stationary data, as the mean changes over time. Now, the data are smoothed, and so the variance remains relatively constant. Now, the trouble with plots like this is that they invite all kinds of conclusions. For example, since both number of democracies and the number of civil wars are increasing, it should follow that the more democracies there are, the more civil wars we should be expecting to see. However, that is indeed a strange conclusion and certainly does not match our intuition and our observation of the world. It would no doubt have a very strange policy implication as well. In fact, if we do a naive OLS estimation, just using democratization to predict the number of civil wars, we get precisely the odd outcome we discussed a minute ago. The correlation is positive, suggesting that more democracies there are in the world, the more conflict, the more civil wars we observe. And the value is 0.7, which is a respectably strong association, since we know that the correlation coefficients range from -1 to 1, we can conclude that the association is indeed quite strong. The regression coefficient for the democratization variable suggests that for every 10 new democracies, we see roughly 4 more civil wars. Again, this would be something to worry about, with truly strange policy implications. So, what is going on here? It turns out that when we model time series data without accounting for time explicitly in our model, we can get effects that do not reflect the world. This problem is akin to that of omitted variable bias, where leaving out a crucial explanatory variable may result in an opposite effect. It can also reduce or overinflate the overall coefficient size, or it can also lead to spurious effects, where we see simple association between independent and dependent variables, while the variables are not causally related in the population and are simply an artifact of our data set. These effects are a result of what in statistics we call an autocorrelation, which means that the errors, or residuals, from our models are not independent of each other. In time series data, the dependence comes from the temporal structure of the data. Practically, we mean that it is very plausible that the number of democracies we observe in the world measured last year will have an effect on how many democracies we will measure next year. Thus, the measurements are not temporally independent. So what can we do about it? We can think through how to precisely model time in our data. Since we have already identified a time trend in our data, in our case, both of our variables are increasing over time, we can account for time trend first by including a year count on the right-hand side of the equation. So now let's take a look at our results in R. We can immediately spot a fundamental difference in our results. Can you see what it is? You're right. The main difference is that the coefficient for democratization is now negative. Thus, it suggests that for every 10 new democracies, the number of civil wars decreases by roughly 2. That is certainly a very different story, and one that probably matches our intuition closer. Now, what can we do next? Are we done with our time modeling exercise? Certainly not. Let's turn to another temporal aspect of our data. Can you identify on these graphs another distinct temporal feature of our data? We have already identified a time trend. Yes, you guessed it. There is a break in our data in the early 90s, suggesting a structural break, associated probably with the end of a large boom of democratization after the end of Cold War, and with the new international system that was created. Can we also model that particular pattern? Yes, there are a number of approaches one can take. We can include a dummy variable that marks the end of the Cold War order. By doing that, we effectively address the difference in intercepts. In our case, the estimated average level of conflicts before and after the Cold War. However, this does not capture our story entirely accurately because we left out the structural changes to the level of democratization in the world with the end of Cold War. So it is also possible that the effect of democratization on civil wars is conditional on whether it occurred during the Cold War or not. Can you suggest what type of model specification could account for these conditional effects? Yes, we can use an interaction effect of a dummy variable marking the end of Cold War order and our democratization variable. Now, the lecture assignment is to interpret the findings by providing manual calculations from the interaction effects. In your discussion board, please also discuss whether you think it was a justified idea to include the interaction effect in this model or not. So now we did all the hard work of theoretical modeling and should check whether we still have autocorrelation in our data by looking at the residuals. We can see that the residuals are clearly non-random, thus suggesting strongly that we still have some autocorrelation left in our data set, in our data. So one approach to addressing autocorrelation is to include a lagged dependent variable on the right-hand side of the equation. We can also double-check our conclusions from looking at two types of tests. The Durbin-Watson test is a hypothesis test for serial correlation or autocorrelation in our data in models where lag was not used. You can see based on the p-value that we can reject the null hypothesis at 0.05 level. Now, in most of the hypothesis tests you have come across so far, this is a welcome outcome. However, in these tests, null hypothesis is that there is no autocorrelation. Thus, rejecting it means that autocorrelation is still likely present in our data. So what is a lag-dependent variable? Practically speaking, you use the past observations of a dependent variable, so in our case, the number of civil wars, to predict the future observations of the dependent variable. You do so by creating a new variable and sliding the dependent variable by 1 year. That is, for example, it is also possible to choose a different lag, 2 years, 3 years, and that depends usually on our theoretical argument. But sometimes it is hard to know what exactly the lag must be or should be to capture the autocorrelation in our data. And so we create a new variable with a lag. Now this new lag dependent variable will be used on the right-hand side of the equation as a predictor. This last model output includes a lagged dependent variable called civ war lag, and this one I lagged by 1 year. The lag civil war at time t-1 variable, now on the right-hand side of the equation, now predicts the dependent variable civil war number of civil wars at time t. And we can see it is positive and statistically significant, suggesting that autocorrelation was very likely the problem. The rest of the model specification is unchanged from our previous discussion. So let's do a final check on the model fit by looking at the residuals from this last model. The residuals do not seem to manifest such a strong pattern as we saw before. And that's the combination of our theoretical modeling, which always comes first, and the inclusion of the lag term has likely reduced autocorrelation in our model. Now we can run the last test to again double check our conclusions from our inspection of the residuals. Since we included a lag in this model, Durbin-Watson test is no longer appropriate. Thus, for our last model, we run Roche-Godfrey test. I hope that I'm pronouncing it correctly. The null hypothesis again formulated as no autocorrelation. So again, in this case, rejecting the null hypothesis would be an undesirable outcome. As you can see, the p-value suggests that we cannot reject the null hypothesis at the 0.05 level. Thus again, it suggests that our reasoning based on the residuals was sound and that we have likely eliminated a substantial portion of autocorrelation from our data.